Dear students, today I will discuss about another misconception, and the misconception is based on electric field. Okay, so what is actually the definition of electric field? What is the conventional definition? Most of the textbook used the definition, and what should be the actual definition of electric field? I will discuss today. Now let me understand what is actually the electric field, or when the electric field is generated. When a rest charge is placed anywhere, then surrounding it a field is created, and that field is known as electric field. But we are interested about the strength of this electric field. What is the strength of this electric field created by this source charge, which is represented here by Qs? And there is a very conventional way to understand that what is the strength of the electric field, or simply what is actually meant by electric field. So to understand the electric field in this region at any point, generally we placed a unit positive charge, that is plus 1 charge. In SI unit it will be 1 coulomb, and in CGS unit it will be 1 stat coulomb. So here plus 1 charge, unit positive charge, which is treated as test charge, is present here. If we kept this test charge plus 1 and we determine the force on this plus 1 charge due to this source charge Qs, then it will be the electric field. Here Fe means the electric force on this plus 1 charge due to this rest charge, that is the source charge, that is the source of this electric field, given by this source of the source of this charge, this source charge Qs is given a force to this 1 coulomb charge, which is the test charge, and that force Fe is treated as the electric field E. This is the more conventional way, and for this case the electric field strength is defined like this, that is force on unit positive test charge, that is force on unit positive test charge due to this source charge. This is the electric field. But on the other hand, sometimes you can see that some textbook use this definition, that force per unit positive test charge, and we will understand that this is more better and is more correct. Actually this is the correct definition of electric field that we should use, not this. We will understand it a minute later. Okay, so here force per unit positive test charge, what it means? It means we have to put a test charge, positive test charge here, that is Q0. This is the any general charge Q0. This is treated as test charge. If we put this test charge Q0 over here, and we have to determine the force acting by this Qs on this Q0, and if we denote this force as Fe, then the force per unit test charge will be Fe divided by Q0. Fe divided by Q0. Force on Q0 is Fe, so force on per Q0 will be Fe divided by Q0. So generally this will be the definition of electric field, that is the force per unit positive test charge, not on unit positive test charge. Here per unit positive test charge means here is a test charge Q0, and the force per unit positive test charge means Fe divided by Q0. And here an important point is that this expression, that limit Q0 tends to 0 Fe divided by Q0, because this test charge should be vanishingly small, or this observed charge should be vanishingly small, because if this is not vanishingly small, if this is large, then it will disturb the position of this charge Qs, and then its electric field, its original electric field will be distorted. If this charge is moving, then this electric field will be distorted. So we have to choose this Q0 or this test charge or this observed charge in such a way that it cannot disturb this source charge Qs, and this is only possible if this Q0 charge is vanishingly small. That is why we have written over here E vector is equal to limit Q0 tends to 0 Fe divided by Q0, or simply you can write it E is equal to Fe divided by Q0, where Q0 is vanishingly small. But here if we use this plus 1 charge, that is if we place this Q0 is equal to plus 1, then it will be E is equal to Fe, that is written over here. But numerically this expression and this expression will give the same result, but physically this is not correct, because if we placed over here a plus 1 charge, that is either plus 1 coulomb or plus 1 stat coulomb, this is not a vanishingly small charge, because in 1 coulomb charge there will be 6.25 into 10 to the power 18 electron. So many electrons are there, so it has a huge charge that is sufficient to disturb this charge Qs. the amount of charge of 1 coulomb is enough to disturb the source charge Qs. So its original electric field will be distorted. So we cannot place over here a plus 1 charge by means of 1 coulomb or 1 stat coulomb charge. So we have to put over here a general charge, that is Q0, which is a positive test charge, and this Q0 should be vanishingly small. This is tends to 0, but plus 1 charge is not tends to 0. You cannot say that the 1 coulomb or 1 stat coulomb charge is tends to 0. So to be tends to 0 a charge, we have to choose a general charge that can be said that it tends to 0. A charge which should be tends to 0, that means it's a vanishingly small quantity. That should not be plus 1 or something like that. So we have to choose over here a Q0 charge, and we have to say that this Q0 is tends to 0. So limit Q0 tends to 0, Fe divided by Q0 is actually gives the electric field of this point, because in that case this Qs will feel no disturbance, but here Qs will feel a disturbance due to this charge. So this type of definition or this types of representation is totally wrong when we talk about electric field or you talk about definition of electric field. Not only this, I can show over here that for point charge, if we apply these two things, this definition and this definition, let me apply this two definition to find out the electric field due to a point charge. Let me take that this source charge is a point charge. Its source charge may be of any type. It may be of a continuous charge distribution, it may be of system of discrete charge distribution, it may be of system of continuous charge distribution. Now let me take the most simple case, that is this Qs is a point charge. Now according to this definition 1, if we use this Qs over here and at a distance r, we have to find out over here the electric field. So according to this definition, as Fe is equal to E, we have to find out the force on this plus 1 charge, that is according to Coulomb's law, 1 over 4 pi epsilon naught into Qs into 1 divided by r square. That is nothing but Q1 Q2 by r square. So this will be E, that is 1 by 4 pi epsilon naught Qs divided by r square. So the numerically this result, and if this is the numerical result of electric field, and we will get, or we have got this result by using this definition. Now let me use this definition 2, that is Fe divided by Q0. So we have to put a Q0 charge over here. So we have to determine the force first. So Fe is equal to 1 over 4 pi epsilon naught into Qs into Q0 divided by r square. Now what will be the electric field? E will be Fe divided by Q0. So we have to divide this expression with Q0, and that will be 1 by 4 pi epsilon naught into Qs by r square, which is same as this expression. So numerically the electric field are same, but the concept is different, because this types of diagram or this type of putting of charge plus 1 charge is totally meaningless, because it will disturb the electric field, or it will force to move this charge Qs, and if this Qs charge is moved, then the magnetic field is generated. If this Qs is moving with acceleration, then electromagnetic radiation will give. So this type of diagram or putting of this type of plus 1 charge is totally wrong. We have to put always this Q0 charge, which is vanishingly small, because only if we put this Q0 charge, then we can set that Q0 tends to 0. But if we take this numerically 1 coulomb charge, then we cannot say that 1 coulomb is tends to 0, because 1 cannot be tends to 0, but a general charge Q0 be tends to 0. So we have to put always this Q0 charge generally. So it will be Qs into Q0 divided by r square. And one more thing is on the unit of electric field, that will also cannot be defined from here, because you can see E is equal to Fe means here the unit of E will be same as unit of Fe. So if you put this expression like that E is equal to Fe, that means the unit of electric field also Newton in SI unit, as force as a unit Newton. But actually electric field has a unit in SI unit Newton per coulomb or dyne per stat coulomb, which is satisfied over here, that E is equal to Fe divided by Q0, that means Newton per coulomb or dyne per stat coulomb. Similarly, we can find from here also, if we take this as the expression of electric field, then it will be Qs into 1. So as this 1 is also a charge, so it will carry a unit. So it will be coulomb into coulomb, that is coulomb square. So it will be coulomb square by meter square, and this is Newton meter square per coulomb square, so it will be Newton. So E will be Newton. But if we talk here that if we divide this by Q0, then the unit is, the coulomb unit is divided. So it will be always Newton per coulomb. If you determine the unit of electric field from this expression, you will always get Newton per coulomb, because there is no charge, because we have divided this expression with Q0, so unit will also be divided. But here we do not divide, we just ignore this term 1 as qs into 1 is into as qs into 1 is equal to 1 qs only, so we just ignore this term. But here there is a unit of charge, coulomb, so it will give you always the unit of force, that is Newton, but here you will get always Newton per coulomb. So in all respects, if you want to say, as well as physically as well as with respect to unit, this definition will always be correct. But the problem is that I have seen many times that the books are written this thing, the force on unit positive charge, they use +1 and they also say that Q0 tends to 0. But if you use this +1 charge, that is 1 +1 coulomb or +1 stat coulomb, then you cannot say that this +1 coulomb tends to 0. So you should not use this type of thing, that is numerical value, that is +1 like that. But if you use the force per unit positive charge, that means the F divided by, per unit means the F divided by Q0, and on unit means the force on the +1 charge. So there is a huge difference between these two languages. Here the force per unit charge, per unit positive test charge, here the force on unit positive test charge. Okay, I have just concentrated this line. You can see many textbook you can see that they use this definition, that force on unit positive charge. But I think this definition is more correct and is exactly correct. Okay, that you can understand from this analysis. Okay, thank you.